Harley Davidson Motor Company proudly presents this PhD Service Training Program. This program is designed to help you provide better service to your customers while you increase your service proficiency, professionalism, and profitability. This PhD program is the third in a series that relates to the handling characteristics of motorcycles. In PhD program number 102, we covered weave and wobble, along with weight distribution and steering head adjustment procedures, and how these affect vehicle handling. In PhD program number 104, we covered alignment procedures for all Harley Davidson models. You might want to review these two programs before continuing with this one. There are three main topics that we'll cover in this program: front-end geometry, how hydraulic and air forks work, and how to properly service the forks on Harley Davidson motorcycles.
Oh no, I can see it already. My high school geometry class with Miss Witcherly.
This is a right triangle. It's called a right triangle because it has a right angle right here, see? Besides, I sent the wrong triangle back to the factory. Get it? Right triangle, wrong triangle.
She was so bad.
Well, this tape couldn't be that bad, could it? Let's watch it and see.
Okay, but you asked for it.
We'll explain what rake and trail are and how they affect the handling of a two-wheeled vehicle. We will also demonstrate how these characteristics change when you modify the front end. We'll take a look at the inside of the fork assembly and give you some tips on how to service them quickly and properly. Let's take a look at the basics of front-end geometry.
Oh no, here it comes.
You've probably heard the term trail. This is the distance between the center of the area where the tire contacts the road and the point where the steering axis would touch the road if it were extended. The steering axis runs through the center of the fork stem. If the trail distance is increased, it will take more effort to turn the front end, especially at slower speeds. If there is not enough trail, the wheel will turn easier, but the motorcycle's ability to absorb a wobble will be reduced. Another term you may have heard is rake or rake angle. This is the angle of the steering axis. It may not be the same as the angle of the fork tubes, but to keep things simple, we'll assume the two angles are the same. If the rake is increased, the steering response will be reduced. In other words, you'll have to turn the handlebars further to go around the same corner. A front end with little or no rake will have a quicker steering response. This means the bike will turn sharper with less movement of the handlebars. This display may help you to understand rake and trail a little more clearly. We've removed the top triple tree to make it easier to demonstrate these concepts. This rod through the center of the steering head represents the steering axis. We can measure its angle with this universal protractor. The rake on our display measures 24 degrees. To show the trail, we've mounted the tire behind the fork and added a plumb bob to the axle. The plumb bob points to the center of the area where the tire contacts the floor. If we extend the rod representing the steering axis until it touches the floor, we can easily measure the trail. With the 19-inch tire, the trail on our display measures 3 3/16 inches. While it may appear to be quite simple at first, the relationships between rake, trail, and handling are really very complex. Each affects the other, and there are no standard formulas. If you change the rake, it's very likely that you'll change the trail, and vice versa. It's extremely difficult to predict how such a change would affect a vehicle's handling. Add to these the factors of weight distribution, steering head adjustment, tire design, riding style, road conditions, and various road speeds, and the design of a good handling two-wheeler becomes a real challenge for even the best of design engineers. Let's relate these concepts to some practical situations. One possible front-end modification would be to install a larger wheel on the front. We don't recommend you do this, but here's what would happen. You'll remember that the rake on our display was 24 degrees, and the trail was 3 3/16 inches. Watch what happens when we install a 21-inch wheel in place of the 19-inch wheel. Our rake has increased to 25 degrees, and the trail has increased to 3 5/16 inches. While this may not seem like much of a difference, it doesn't take much to have a noticeable effect on the vehicle's handling. To complicate things a bit more, we now have a wheel and tire with a different weight. And as we showed you in PhD program number 102, even the slightest change in weight on the front end will have an effect on the vehicle's handling characteristics. Changing a front wheel like this is only asking for handling problems. Even though the factory may have offered models with front ends similar to this one, other changes are usually included to ensure a safe handling vehicle. To be safe, keep it stock. Another modification would be to install extended front forks. Let's go back to our original wheel, but this time we'll extend the forks by 5 inches. This increases the rake to 30 degrees, a considerable jump of 6 degrees. The trail also increases significantly. Now it measures 5 1/8 inches, an increase of 1 15/16 inches. Changes like these will have a significant effect on the handling characteristics of any two-wheeled vehicle. Then there's the effect of the extra weight of the longer fork tubes. A front end like this is likely to be difficult to handle at slow speeds and in corners. It's a risky modification at best, a risk you should not take. Even if the bike handles acceptably in this condition, you don't know how it will behave if the rider adds some accessories or changes the tires. You could be on the borderline of a potential handling problem if you don't follow factory recommendations.
I think I follow that. It seems pretty clear, but can we go look at that on a bike?
Sure, anytime.
Now the trail is measured from where the steering axis would touch the ground to the center of the tire contact patch. And the rake is measured like this.
You got it right so far.
And he said that if you install bigger tires or longer fork tubes, you're asking for trouble. Well, how do Butch and Joe survive with their machines all modified like that?
Well, those guys are very lucky. You see, there are so many things like rake and trail, steering head adjustment, weight distribution, tires, road conditions, and so on that affect the way a bike handles. It's just impossible to tell what could happen, especially in an emergency situation. Besides, you don't know what the customer might do to it later. And if someone gets into an accident on a bike that you modified, you could be facing a serious problem. Come on, let's go watch the rest of that tape.
The front ends on Harley Davidson motorcycles are carefully designed to provide good handling vehicles. While modifications such as oversized wheels or extended forks may be popular, we don't recommend you try them. The results are unpredictable, and the risk is very high. Keep it safe. Keep it stock. Of course, the purpose of the fork is to absorb bumps so the rider can enjoy a smooth ride over a wide range of road surfaces. We use springs, air, and oil to do this. From the outside, you can see two main components, the fork tube and the slider. The space inside is filled with about 2/3 air and 1/3 oil. Now, Let's take a look inside. As you can see in this cutaway, the main spring is inside the tube. It's held in place by a plug with an O-ring to seal out dirt and seal in the air and oil. The boot and seal provide the same protection for the slider. A spacer provides support for the seal, while a retaining ring holds it in place. Two bushings provide bearing surfaces for the slider to move along the tube. The upper bushing is fixed inside the slider, and the lower one is attached to the tube. Bolted to the bottom of the slider is a damper tube. The piston at the top supports the main spring. The nylon rings on the piston help control the oil as it flows between the slider and the fork tube. This part, painted blue, is a one-way valve that also controls oil flow inside the fork. It's held in place by a sleeve, painted yellow, pressed into the bottom of the fork tube. Between the one-way valve and the damper tube piston is the rebound spring. It cushions the fork when it reaches its full extension. Greatly simplified, the main spring controls the height of the bike while riding. It compresses when a bump forces the slider upwards. Air, which occupies most of the tube, also controls the height of the bike. It too compresses to help absorb road bumps. Oil fills the slider up to just above the damper tube. In addition to lubricating the fork, the oil dampens the action of the springs and the air. That way, the front end doesn't bounce excessively. Unlike air, oil cannot be compressed. So when the slider is forced up by a bump, this oil is pushed up into the fork tube. By controlling the movement of this oil, we can control the dampening effect it has. Here's how it works. There are 3 compartments in the fork assembly. The top one contains mostly air, with about an inch of oil at the bottom. A much smaller compartment in the bottom of the fork tube contains only oil. The piston rings on the damper tube seal off the top of this compartment, while the one-way valve closes off the bottom. The third compartment is in the bottom of the slider, and it too contains only oil. When the fork is compressed, oil is forced out of this compartment through the 2 large holes near the bottom of the damper tube. It travels up the center of the tube, out the top, and into the fork tube. The air in the tube is compressed to make room for this oil. Oil is also forced up through the one-way valve into the second compartment. This compartment is getting bigger, allowing it to take on more oil. It's the one-way valve and the size of these 2 large holes near the bottom of the damper tube that control the dampening action when the fork is being compressed. You can upset this fork action in 2 ways. One is to use a thinner or thicker oil. Thicker oil, because it flows more slowly, will increase the dampening action, while thinner oil will reduce the dampening action. Also, raising the oil level will reduce the airspace needed to allow the fork to compress, making it too stiff. Too little oil will make the fork too bouncy. In an extreme case, when hitting a very large bump at a higher speed, for example, the fork may bottom out or reach the end of its travel. When this happens, a stop in the bottom of the slider and the sleeve in the bottom of the fork tube combine to trap a small amount of oil. This trapped oil is known as a hydraulic lock, and it prevents damaging metal-to-metal contact of the fork components. Remember that oil cannot be compressed, so the rider will feel a pretty hard knock when it happens. In most instances, the compressed air and spring are able to overcome the upward movement of the slider before bottoming occurs. At this point, the fork extends itself. Here's what happens inside. The air pressure in the fork tube pushes the oil back down the center of the damper tube and into the slider. The center compartment is now getting smaller, so the oil in there has to go somewhere. The piston rings seal off the top of this compartment, and the one-way valve won't let the oil out the bottom. The only way for this oil to get out is through two small holes near the top of the damper tube. It's the size of these holes that control the dampening action of the fork during extension. The oil then travels down the tube and into the slider. If the fork should become fully extended or top out, the rebound spring cushions the impact. Also, the one-way valve passes the small holes in the damper tube, trapping a small amount of oil. Once again, this trapped oil or hydraulic lock prevents damaging metal-to-metal contact. Air forks aren't much different from standard hydraulic forks. Basically, they have more airspace and, on Harley Davidsons, a true anti-dive mechanism. This is how it works. On 1988 models, the handlebars provide the extra airspace. And because it's compressible, this air helps the forks absorb the bumps better. This air is slightly pressurized, so the ride is not too soft. On the other hand, too much air pressure will make the forks too stiff. A hose connects the handlebars to a manifold, which joins the two forks. A solenoid valve in the hose line cuts off the extra airspace when braking. It's activated when either brake light switch is activated. With the extra airspace cut off, the air in the fork, which is still pressurized, actually makes the fork stiffer than the standard hydraulic fork. The result is a true anti-dive front end. On 1987 and earlier FLT models, the engine guard provides the extra airspace. 87 and earlier FXRT models used a special accumulator. A bladder inside divides the accumulator so different air pressures can be maintained in each portion. While pressure in the forks is about 8 psi, pressure on the back side of the bladder is about 30 psi. When hitting a large bump, air pressure in the fork exceeds the air pressure captured behind the bladder. At this point, the captured air helps absorb the impact of the bump. Increasing air pressure in the fork increases both riding and anti-dive stiffness. Increasing air pressure in the back of the accumulator increases riding stiffness only.
So that's how that works. Air forks are practically the same as regular forks, except that they have more airspace.
And the solenoid cuts off that extra space when either brake is applied. That's why the front end doesn't dive as much when you do a hard stop. The rest of the components are pretty much the same.
Let me see if I can remember them. There's the main and rebound springs, the tube and slider, the damper tube with piston and rings on top, and those two bushings that let the slider move along the tube.
And don't forget the seal and dust boot to keep the dirt out and oil and air in.
Right. The air and the mainsprings support the bike and absorb the bumps. And the oil dampens the spring action so it doesn't bounce like a pogo stick.
I like the way they use that one-way valve to control the oil flow between the compartments.
Yeah, that's pretty slick. But what I thought was a real trick is how the oil gets trapped at the end of the fork travel so there's no damage to the parts.
Yeah, that's a new one on me.
You mean there's something even you don't know?
That's why I watch these tapes. Come on, let's roll it.
Now that we've covered the components and how they work, let's go over the service procedures. The first thing is to let the air out of the forks on all air fork models. If you don't, you're asking for a shower when you drain the oil. Remove the brake calipers, fender, and wheel. If you're not familiar with these procedures, refer to the service manual. Slide up the dust cap and seal. Service only one fork leg at a time to reduce the chances of misadjusting the steering head. Remove the air manifold bolt and loosen the fork tube plug. Loosen the top pinch bolt if there is one. Loosen the lower pinch bolt and slide the fork leg out of the triple trays. On models with fork tubes that are tapered at the top, you'll have to tap the tube loose from the upper triple tray. On models with 41mm forks, remove the cap, loosen the lower pinch bolt, then slide the fork leg down slightly. Tighten the pinch bolt so the tube won't turn. Then loosen the plug. Remove the spring and pour out the oil. If the spring is distorted or cracked, it should be replaced. Remove the damper tube bolt from the bottom of the slider. Use an impact wrench since the damper tube is likely to turn. You'll need a long 6mm hex drive for this bolt. Remove the retaining ring. With a slide hammer type action, pull the fork leg apart. If the base metal shows through the surface material of the bushing, it should be replaced. This applies to the outer surface of the lower bushing and the inner surface of the upper bushing. Replace the bushings in pairs. Before reassembling any components, make sure they are clean and coated with fresh fork oil. Gently slide the lower bushing into the groove on the tube. The nylon piston rings should be replaced if they are damaged or show signs of wear. Do not reuse any of the O-rings, seals, or copper washers. Insert the damper tube with the rebound spring installed into the fork tube. Then carefully slide the fork tube inside the slider. Tighten the damper tube bolt using an impact wrench. Slide the bushing over the tube, followed by the spacer with its concaved side, if there is one, facing the bushing. Next goes a new oil seal with the numbered side facing away from the spacer. Use the fork seal installation tool to seat the bushing and seal in the slider. Install the retaining ring. A new dust seal and the cover. Use an old O-ring and the seal installation tool to prevent damaging the cover. Add the proper amount of fork oil as listed in the service manual. Use the amount listed for a dry fork. If the spring has a taper, the tapered end goes at the bottom of the tube. Except on models with tapered tubes, install the plug hand tight. On models with tapered fork tubes, install the leg all the way into the triple trays. Then install and tighten the fork tube plug before tightening the pinch bolt. This will prevent binding the steering head. On other models, install the assembly in the lower triple tree only and clamp it firmly. This will hold the tube so you can tighten the plug. Reposition the fork leg to the right height. Then tighten the pinch bolts to the proper torque. It's important that both tubes are at the same height. On FLT models, again, Tighten the tube cap before you tighten the pinch bolt. And don't forget the rubber sleeves. Now, you're ready to do the other side. When both sides are done, install the air manifold, wheel, fender, and brake calipers, making sure you observe all specifications and warnings given in the service manual. On all air suspension models, use the no-loss air gauge to set the pressure level in the handlebars. Do this with the bike on the jiffy stand. You'll find the pressure specifications in the service manual. Before removing the gauge, grab the front brake lever and bounce the front end with the ignition turned off. The gauge should fluctuate, indicating that the solenoid valve is open. Turn on the ignition, and with the brake applied, bounce the front end again. This time, the gauge should not move, indicating the solenoid valve is closed and the anti-dive system is working properly. On earlier FLT models, set the pressure and check the solenoid at the engine guard. On FXRT models with an accumulator, check the pressure on both sides of the bladder. Check the operation of the solenoid valve with the gauge on the accumulator as well. If the solenoid fails this test, check the service manual for further test and service procedures. The front forks on all Harley Davidson motorcycles are carefully designed to provide superior riding comfort. With proper maintenance, they are virtually trouble-free. Service is simple. With a front end like this, why would anyone want to change it?
That was pretty good.
Yeah, now for the fun part. You want Form A or Form B?
I'll take Form B this time. Say, boss, no doubt you took geometry in high school. Who'd you have?
Miss Wycherley. Who else?
You too? She was so bad.
This PhD service training program was designed to help you provide better service to your customers while making your service operation more proficient, professional, and profitable. For additional training, attend the courses offered at the Harley Davidson Technical Training Center. Call the service department for more information. This program was produced by the Harley Davidson Service and Technical Communications Departments.